Solving exponential equations. A little recap of what we've done so far. Eventually, we're going to be turning to page 420. So if you want to make some notes at the top of page 420, that would be fine. So far, first of all, how do we recognize an exponential equation? An exponential equation is one where the x is in the exponent, like 4x equals 31. Or I might have more than one x. 3 to the x plus 1 equals 9 to the x squared. Something like that. In any of these situations, the x is in the exponent. And if the x is in the exponent, you have an exponential equation. And so far, we have learned two techniques for solving exponential equations. So what I want you to be able to do is, first of all, recognize an exponential equation. And it's one of the easiest to recognize because the x is in the exponent. And then, whenever you're given an exponential equation, I want you to think of the two methods that we've learned already to solve them. And generally, they fall into two categories. The first method we learned was a non-calculator method. I'll put a 1 here since it was our first method. And that was just where we got the bases the same. So we used our powers chart, and we had to get our bases the same. And when you were working on that sheet the other day, when you got to question 5, I said, can you solve that one without logarithms? That's because it was one that you could get the bases the same. And these ones look something like this. You might have 8 to the 2x equals 32 to the x plus 1. And the fact that you can change both the 8 and the 32 to bases of 2, then you just need to use your exponent laws to get a single base of base 2 or a single power of base 2 on both sides, and then you could solve it. Oh, it's just too tempting just to leave like that. Let's solve it all. So here on this side, you would multiply, so we get 2 to the 6x equals, here you would multiply 2 to the 5x plus 5. And at this moment that you've got both powers with the same base, so you could just write that 6x equals 5x plus 5. And we get that x is equal to 5. That was our first method. And that method will often appear on a non-calculator part of a test or exam because you didn't need your calculator to solve it. But there are times that you can't get the bases the same. So those ones always appear on calculator sections of your exam. And that's the second method that we learned, where you used logs to help you solve them. An equation like this one, we can't get the bases the same. And so then we have to use logs or natural logs or logs of any base to help us solve it. And the way that we go about solving it is we start by taking the log of both sides. And I would take that step. Sometimes that step on its own is worth a full mark. Sometimes it's worth a half mark on the exam. Don't try to do too much with your log laws at once, because as soon as you make a mistake with logarithms, it can be catastrophic leading forward. So I take the log of both sides. Now my x can come out in front here. My 2x plus 3 can come out in front here. What mistake did I make? No mistakes? Should just keep going? Okay. When you bring this 2x plus 3 out in front, since it's one big thing, you'll need brackets around it. Now log 3 is a number, log 5 is a number, and this is something that's going to be very important, especially moving forward in period 3 today, is to recognize when something's a number. So you have to ask yourself, if I type this into my calculator, would a number appear? If I type in log 5 and push enter, does a number appear? Yes, because log 5 means 10 to what exponent would be 5. It'll give you 0 point something, but it is a number. And because it's a number, you're allowed to distribute. And so we get x log 3 equals 2x log 5 plus 3 log 5. And from your practice yesterday with solving for logarithms, these questions that have x's, more than one x, those are like terms. You'll want to get them on the same side of your equation. So I'll subtract 2x log 5 on both sides. And when you have more than one x, and once they're on the same side, you can factor out that common factor of x. And once you've done that, you can divide. And this is where the calculator comes in. You can type this entire thing into your calculator to find your answer. So I would use the fraction button if you have it every single time with logarithms. So you want to go log of 3 divided by log of 3 minus 2 log 5. We get negative 0.518. I'm going to store that as x. And then if I look back at what my original equation was, it was 3x is supposed to equal 5 to the 2x plus 3. So what I can do to check is I can say, well, I just stored my answer as x, so what is 3 to the x? And what is 5 to the 2x plus 3? Are they the same? No. So where did we make our mistake? What went wrong? Okay. So from here to here, and nobody mentioned this? I just decided to miraculously, or did you think it was some new fancy math? You guys are so quiet, right? Catastrophic mistakes happen when you're quiet. Everything went wrong. So what we can do, we'll go back and fix this up. Was that when Azar came late? Is that why we made the mistake? Oh man, that's on video. You can watch that over and over again. Okay, so this should be 3 log 5 up here, and now we're going to check again. But again, this is what's really nice about using our calculator, is that we can check if we've got it right or not. And it can be very exciting on a test because you'll know right away if you got it right. It can be also very disappointing on a test when you recognized you made a mistake as crazy as this. At least in this case, it was easy to find. So now I'm going to retype it in with the fraction button, 3 log 5 log 3 minus 2 log 5. Get a new answer, going to try storing that one as x, and now we're going to attempt again to see, did we do everything right, or did we make another mistake somewhere? And sometimes when you make a mistake and try to fix it, what's going to end up happening is you're just going to keep making mistakes. So sometimes a good strategy in math, if you've made a mistake, tried to fix it, and you still make a mistake, and it's still not working, take a deep breath and start again. It's going to be faster because sometimes when you start erasing things and mixing things up, you end up making more and more mistakes. So now we're going to see if we go back to our original equation here, does it work? 3 to the power x is now 0.08, and 5 to the power 2x plus 3 is 0.08. Good, because I didn't really want to restart the whole thing and do it all over again. But it's very nice because you can check to find out if you're right. But that's what a calculator question is going to be. And if we turn to example 3 on page 420, there's 3 examples here. Now, for each of these examples, they each show something a little bit different. We're actually going to skip example C because example C is very similar to the one that we just did here. But I want to show you some things with example A and example B. I'm going to show you them in a regular solving way, and then I'm going to show you some other things that you could maybe do that might make it easier. Okay? So for A, it's an exponential equation. We have 2 techniques. We can either get the bases the same or use logs. So your first thing that you're doing always when you approach a question is ask yourself, can I get the bases the same? Can I do this without my calculator? I've got 12 and 4. Do they appear in the same column of a powers chart? If the answer is no, then you're going to have to use logs. So in using logs, we have to take the log of both sides. And what we can do, log of 12 equals log of 4x. And some of you, when you get better with logs, might go right away to this step and say, I took the log of both sides, and I'm going to bring the x out in front of the exponent. Again, be careful with that, because if you're doing too many steps at once, your chances of making a small mistake do increase. And we don't want you to make any mistakes. But now you can divide both sides by log 4. You can type this into your calculator. Log 12 divided by log 4. Get your answer, store it as x, and check 4 to the power of x. Does it equal 12? Yes. Okay, and it's okay to do that even during the exam. You solve your log, you check it, it's right, you feel that relief that you don't have to redo the question, you can let out a little exclamation, yes, a little fist pump during the exam or during your test or even during your homework. That's okay. So yes, we got this one right. Now, most of you will solve things this way, and this is great. What I want you to see in this one is that with very simplistic equations like this one, we could have, and I'll do it in blue, also use the definition of the logarithm. And the definition of the logarithm says if I want to change an exponential equation to, oh my goodness, a disaster. Come on. There we go. If I want to change an exponential equation to a logarithmic equation or a logarithmic expression, in log form, the base is 4. The answer is 12. Logs solve for exponents. So if I just write 12 equals 4 to the x using the definition of the logarithm in logarithmic form, I get log base 4 of 12 equals x. And if I do that and go to my calculator and go to number 5, log base, and type in log base 4 of 12, notice I get the same answer. So using the definition of the logarithm here is even faster than taking the log of both sides. Should we always use the definition of the logarithm? No, it only works in these simplistic ones. And so in that case, this one, it's nice to use that for a shortened form. Also, if you only have a TI-83, This is great, but then you would need to use the change of base theorem that we learned yesterday. And do you remember that you could change log 4 of 12 to log 12 over log 4? Especially if you have a TI-83, you're like, yeah, I need to know that. So in that case, it's not that much faster. If you have a TI-83, I'd probably just say take the log of both sides and solve it like normal. But the change of base theorem comes into play, and you could use the definition, could be a little bit shorter. So that's something that part A helps review for us. Part B. In part B, we've got an exponential equation. We've got a whole bunch of extra stuff. Chances are we can't get the bases the same. We're going to take the log of both sides. Now in part B, what I'm going to do is instead of taking the log of both sides, well, I'm still going to take a log of both sides, but I'm going to take the natural log of both sides. So I'm going to take the natural log of this side and the natural log of this side. And the reason I'm going to do this is to show that it doesn't matter which log you take of both sides. I could have taken log base 3,852 of both sides in the first question. I just would have had to write 3,852 every time I wrote log, and it would be annoying and take longer. And it would be annoying to type into my calculator. But it would have worked. And so when I take the natural log of both sides, it's going to work. Now, this question has temptation built into it. You are going to be tempted to multiply 3 times 2 and get 6. But you have to remember order of operations. We can't multiply before exponents are dealt with. And so with this multiplication here, we use our log laws and say, well, I know I have a log law that if I multiply inside of a logarithm, that's the same as adding 2 logarithms. And so my equation becomes natural log of 3 plus, and now that exponent can come out in front. That's the other temptation you're going to have with this exponent here. You're going to want to bring the exponent out in front early, but you can only bring an exponent out in front if that exponent is to the entire base inside of your logarithm. And so in the beginning here, which I underline here in purple, this x plus 1 is an exponent just to the 2. It is not an exponent to the 3. And since it's not an exponent to the entire thing, we're not allowed to bring it out in front using our log law. But now that that exponent is to the entire thing, I can bring out that x plus 1 in front. Is natural log of 2 a number? If you type it into your calculator, will you get a number? Can I solve that mental math? E to what exponent would be 2? Be just a little bit less than 1. So this is a number, and because it's a number, I can distribute. So I'll have natural log of 36 equals natural log of 3 plus x natural log of 2 plus natural log of 2. Whew. We want to solve for x. I only have x in one place. So just like solving normal equations, you're going to want to put your like terms on one side. I'm going to move all of these numbers. Natural log of 3 I'm going to subtract, natural log of 2, and get the term with the x all by itself. And then finally, I can divide everything by natural log of 2 to get x by itself. I go to my calculator, and on my calculator, again, use my fraction button. Natural log button is right underneath the log button. Natural log of 36 minus natural log of 3 minus natural log of 2, all divided by the natural log of 2, 2.58. And actually, on your exam, you have to round to 3 decimals when it doesn't say so, 2.585. Now we're going to check what was my original equation here, 36 equal. So I'm going to store that answer as x, and I want to check if 3 times 2 to the exponent x plus 1 is equal to 36. It is. Yes, little fist pump. A little bit of excitement there. We got our answer right. Okay? Now, I use natural logs because it doesn't matter if you use natural logs or logs. But look how many times we had to write natural log. If we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. In the end of this question, we wrote ln 20 times. So by choosing ln as opposed to choosing log, we saved one letter 20 times. That might save you, 3.25 seconds on your exam, which you can use to check over things or just be a little bit more relaxed. So sometimes natural logs are nicer just because you can write them faster than writing log every time. Although they feel a little bit more uncomfortable because they're like, ooh, it's a base E. I don't like E because it's like a weird number. So I like log because it's base 10 and that's calming. If that's the case, use logs. It does not matter.